Yeah, hi, thanks for joining me here, and thanks for coming. I'm going to talk today about my current project I'm working on. I'm currently contracting for an APM tool vendor. And APM, I don't know if you guys all know what it is. So I'll just ask, who of you have used like a tool like New Relic, App Dynamics, Dynatrace, these sort of things? Are you guys, oh, we are started, right? Are you guys using these sort of things? Right, okay, so what I'm trying to do here today is I'll try to explain to you how these tools work. I'll try to explain to you some caveats these tools have, and I'll show you how you, in theory, can implement your own tool even, if you wanted that. That said, I'm contracting, as I said, for a tool vendor, and I'll show some product slides which aren't intended as a sales pitch. I'm not a salesman, I'm not paid even to do these things, but I can't talk about my work without talking about my work, so I hope you forgive me. I just wanted to make this explicit such that nobody thinks I'm trying to sneak sell you something, right? So, okay, but before I talk about APM, I wanted to take some inventory of the Java ecosystem, how it looks like in the enterprise world today, and I hopefully can explain to you by doing so why APM tools have become so popular over the last years. So we came from the enterprise world, right? You guys might have been doing Java EE for years, where you had EARs and you deployed them. You deployed them in a container. And if you try to scale your application, for example, if you try to write distributed systems, Java EE offered you APIs for that. So you could deploy different nodes on different machines, and these nodes would communicate on standard APIs, and things would be pretty much pre-configured. So if a web request came in, a ready node would answer that web request, and you could choose in a way to just think about your application, or at least that was the promise of Java EE, that you just write your application, you deploy it, and then you have these great dashboards, right, where you can configure them and where you can build clusters and all these things. And this is where Java EE comes from, right? And in this world, we already had some means of configuring distributed applications, like microservices we had today. Java EE, in a way, offered the same semantics. You could configure clusters, you could spin up new nodes, and in theory, this is how these heavyweight servers were sold, right? And I think this is a basic misunderstanding of Java EE that developers have, that Java EE is a promise to the operations, mostly, and not to the developers, right? So WebSphere and WebLogic, that's what their sales point was, right? You build your app, and deployment is more or less automatically, or not deployment, but operations, right? And you already had distributed tracing in these things. You would know how your services interact. You could open these dashboards, and you could see one web request comes in, talks to node A talks to node B, and if something goes slow, right, and something goes slow in node B, you could see in this dashboards what was going wrong, right? But we don't want this anymore, right? We as developers, we think Java EE today is not the hip thing, the cool thing to do anymore. We like to write greenfield projects with a public static void main. We like to write a drop wizard app, right? We like to use Vertex, use Spring Boot, and deploy this in the network, and then we have microservices, and they talk to each other with HTTP. And this is great for development, and I've written apps like that myself, and it is nice. You don't have to think about standard APIs, you don't have to download a 200 megabyte application server to run a simple hello world, right? These things are great in this way. And we have these services, but if a web request comes in, it is much more complicated now. These apps talk rather randomly with each other. We have HTTP protocol buffers, sometimes binary protocols. People use Netty a lot, implement their own stuff. And this ends up in very complex networks of services, right? In Java EE, we had these dashboards, but with microservices, if we write public static void main apps, it's much more difficult to understand how these services interact. And this is a overview of how Halo services work with each other. This is all of the services in a circle, right? And the lines connect the services, how they talk to each other. And the green lines are in a way the highways, right? And for operations, this is much harder. With Java-E, you still had a dashboard, but right now, Baruch in the other room. Right, so, and this is just Halo. This is Twitter. Twitter has a microservices architecture, and think about how complex it must be to run this thing in production. Think about how difficult it is to debug a performance problem at Twitter if these services talk to each other, right? And we already found a term for this. This is so-called Death Star architecture, because while microservices are easy to develop, you gain a lot of complexity in operations, and that's kind of the trade-off. And that's where we are, and this is where we're heading, right? Because with microservices, you can't just say, okay, let's just shut down the system and spin it up again. Hopefully all of the problems are going away. And this is where APM tool vendors market so much, and that's why you see so many commercials everywhere. It's becoming a big, big market to sell solutions for monitoring microservices, or for not necessarily microservices, but for monitoring systems and interactions that don't interact on standard APIs, right? Because operations gets hard, and this is also why DevOps is on the run, because these systems require so much knowledge of how the system works in order to operate it, that this just becomes a necessity. And as a matter of fact, this is not really what I'm here to talk about, but just where we're heading, right? We still want to build jars, but we deployed an AWS Lambda, for example. These new sort of serverless architectures, in a way, they have the promise of bringing us a bit back to Java EE, because then again we have dispatches, and again these are, in a way, provisioned automatically by Amazon, and then when a web request comes in, we again work against standard APIs. So this is, for me, it's a bit funny to see for our industry, we're going in circles all of the time, right? Because AWS is nothing but Java EE in the cloud by Amazon with a different API that actually knows how to do less. So this steady trade-off, this is something we have to work with, and right now with the microservices age, we need monitoring from the outside, and this is how these tools try to help you, and this is why it's, in my opinion, also quite important to understand how they work. This just is a takeaway, there's no silver bullet, obviously. Also microservices have their struggles, and understanding how microservices interact, that's one of the biggest problems we have. So let's look into this. Let's look into how we want to monitor microservices and why it's important. So let's think of an example application. Let's think of this app here, which is just some server running a food jar. And this food jar receives a web request from the internet, right? There's a HTTP call coming in. And in modern applications, this food jar isn't self-contained. The food jar has to communicate with outside services in order to be able to answer on a web call, right? So let's say foo is a front-end server. It shows you a web page or something. But in order to serve this web page, foo needs information from some application server in the back end, which is bar. Bar processes information, and they communicate via HTTP as well. And in order for bar to answer to a question, it has to go to a MySQL database. And just as an example, let's say this MySQL database is overloaded. It's serving too many requests, and it's slow. So this application here is broken, or the connection between bar and the database is broken, and it needs some different configuration. So we as a developer would need to go into the system now and maybe give it more processing power, or give it more RAM, I don't know, or free some memory in order to make the application run fast again. Because right now our users are observing latency in their requests, right? However, what you observe is that your users are exactly doing that. They have latency in their requests. So how can you find out that it's the database? Because this just propagates down, right? You see slow answers from foo. So you have to find out how this is actually happening, and that is the database that's causing this. And one very common approach, and all APM tools in a way implement this, is tracing. And a lot of the big companies like Uber or Twitter, they all have written frameworks in order to allow you to implement such tracing. If you have heard of Zipkin or OpenTracing, Jaeger, all these frameworks, or FineAngle also from Twitter, they are built with the intention to allow you to understand how web requests interact. So how does tracing work? Well, tracing basically sends information about machines being entered and exited from the outside to some form of server, which is a trace collector. So whenever a request comes in at foo, we want to record when we enter this machine, when the outside request comes in. And we also want to note down when we exit this machine. So we basically record this entry, and we also record when we basically send back the answer. Right? So we know how long it took to serve a HTTP request. That far you can do just logging, right? You can have a log, answered this IP in that and that many milliseconds. It's easy enough if you have like a servlet to just have a system out println statement in the most trivial case. But in tracing we just want to have this noted like as a JSON file, JSON somehow, and give this trace an ID, this one event. But we also want to write down that we exit the server to make a call to some other machine, which we have to wait for before we can answer our original request. So, given that, we have already, now we know that we entered foo with this trace A, and then we made a request to B. So now we want to do the same thing for the other machine, right? So bar also just writes down when it gets a request from the outside and when it answers this request. So, but the problem here is that HTTP is a stateless protocol. We can't really tell that these two requests connect to each other. But we can do that by adding just a header. So we have a unique ID for the first trace, the first event here where we entered and exited foo. So we just want to add information to the HTTP header such that B knows that this call is actually not coming from the outside, but from an internal service. And since this unique ID is now known to B, it can basically tell the trace collector, I am now serving a request from foo, and I'm doing this now, and it took me that and that much time. So in a way, we can tell that the exit from foo and the entry from bar are connected. So we can merge these two spans here, and we will not observe the same times, right? This is also the trivial idea that you say you match it by timing, but we have network latencies. We have measurement inaccuracies, right? This is something we have to take into account, and this is why we need this explicit fingerprinting of every call, and then we can merge it. And now finally we can say, okay, bar is actually making a JDBC request to the MySQL database, and that takes so long time, and that's not supposed to take that much. So now, with all this information, we basically can look, okay, we started out here with a request at 0 milliseconds coming into foo. This triggered a request at bar. We have that and that much network latencies, which are the light blue things there, which then triggered a MySQL request. And these three things are connected. It's happening on different machines, maybe even on different hardware, but it's all one flow, right? And this is what distributed tracing is. We can, now that we have collected this information, render that in some front end, and that's what Zipkin does, that's what all the APM tools are doing, and this is how it's done. It's very tedious because you have to add this to every HTTP call in theory, but you get the information that you want, and this is the information that in Java-E in the old days you had automatically, because the servlets were served by the Java-E container, right? And then obviously the Java-E container couldn't do all these things for you. It could fingerprint every request, and it would know when it would communicate with another node, because that was done using Corba or something, right? And there you could also just say, I'm asking you now something for request with ID that and that. And I mean, my opinion, to be perfectly honest, the whole lightweight Java-E movement, that's what put the end to it as well, because the good parts went away, all the operations overview that you got from EE, and but you still had the constraints that the standard API gave you. So in a way, I wonder sometimes if that's what the problem was. And I know how tough it can be to work with WebSphere or WebLogic as a developer, but in production they sometimes actually are not so bad. So how do we get this information? Well, and the standard that is used today is Sipcan, which is a framework Twitter has created, and Sipcan is huge. Sipcan is, I would say, the biggest tracing framework in the world, and it does exactly what I just discussed. In order to describe these spans, you have like server requests and you have like server send. So you know when you entered and you exited the machine, you would just take a timestamp every time these events happened. You would put it in a JSON and you would send it to a server. And then the server collects all these so-called spans on every machine, creates spans, and then you create them together into a trace. And a trace is one request, and a span is basically the passage through one machine. And with the Sipcan model, you can also annotate every span with random information, like you can say, okay, this is my SQL call, this was a query doing select one from dual, and then you would be able to go into your GUI and see what happened. This is how Zipkin looks like in the front end. It's open source, it's for free, Apache 2 null license, so you can download this and you can use it, of course. And this is what you get out, right? Here you see it's not the best quality, but you know what it is supposed to be like, right? I showed you something similar right now. Those are just a much, much deeper call stack, which is, that's what you can think of it as an analogy. It's a call stack distributed over machines. That's what it generates. So, but the big question still is, how do you generate this sort of call stack? And you do it by coding it into your app. So whenever you, for example, you're having a servlet application, so you would add a servlet filter that once you enter the machine, you start creating a span. And then you have the span builder and you give it a trace ID, and the trace ID is basically the unique ID that goes over all machines, and that you typically have within a HTTP header. So in a filter or in a servlet, you would check if the servlet request has already this header, and if it has this header, the value of the header would be a unique ID, and you would just reuse that one. And then you give it just a random ID, which is probably randomized on your machine, or you have some pattern, it's up to you, and you might give it a name, and you will want to record the timestamp of when you entered. And then you do something. You create the response for this request, and after you send it, or right before you send it back, you would say, okay, you know what, now I'm done. Now I want to record the time it took to do that, and then in addition, you would send it to the backend server. So by wrapping or by adding this filter to your servlet API, every time you would serve a request, you would send this information, and then you could see this information in your Sipcan front end. So this would be the start, and this would be the end. Together, you would have a duration that you can measure. And Zipkin or Brave that Twitter wrote is basically, Brave is a Java implementation of Zipkin is the framework, the idea, the specification in a way, and Brave is the implementation by Twitter of the specification. You would have to do this, and some libraries have it built in, and most popularly the libraries that are distributed by Twitter and by Uber and all these people that are really, really dependent on tracing because they have so many services that otherwise they couldn't do their production work anymore. So like, for example, FineAngle, which is a Twitter RPC framework, is built in with Zipkin. So RPC, you just say, I want these traces to be generated. This is the IP address of the server you should send the information to. Right? And there's multiple APIs for all languages, for Go, Java, .NET. So you can also do this cross-platform, right? So you can have a Java app that talks to a .NET app, still, as long as both applications send their information to the backend server, you would have these distributed call stacks that you want. The problem, though, is that Zipkin is an implementation, and it's not lightweight exactly, or Brave as well. So people sometimes struggle, and that's the biggest challenge with it. It's maybe not you who's creating servlet requests, or it's maybe in some library code that you don't control. So you would need to ask everybody, and basically that's the Twitter approach right now. They would go around and ask everybody, please offer that you generate these traces. So they basically ask all the big HTTP framework vendors for all platforms in the world, please generate these spans and allow them to be sent. And the initiative is called OpenTracing. So a Java implementation of OpenTracing is basically, again, just an API, which if it's not existent, it's a no operation. It's like simple log4j, but distributed tracing, right? So you would create a span, then you would do the work, and then you would finish the span. And this stuff has been around for a couple of years now, and probably a lot of you only hear of this for the first time right now. And this is a general problem with standards, right? You might notice comic here. People have ideas how things should be done, and then they introduce standards, and then other people disagree and they introduce their own standards. In the end, you have a lot of standards, which breaks the idea. And in my opinion, that's what's happening, unfortunately, in the distributed tracing space. Distributed tracing is still pretty difficult because we can't agree on something, and I don't think this is the way to go. And if you have heard any of my talks before, you might know that I do a lot of like bytecode manipulation things. This is also the reason I'm contracting for this company right now. This is the other way of doing it. This is what I want to show you, how you can do distributed tracing without Zipkin today. So most distributed tracing talks are about Zipkin. I think I know a better way. I'll show you. So what I've been doing for the last 8 months now is implementing this sort of distributed tracing for Java applications, for any Java application. And we do this by writing a Java agent, which looks like that. I don't know, have you guys worked with Java agents before, or do you know what Java agents are? A couple of people, perfect. Unfortunately, it's so dark. I don't know how many people raised their arms now, but I'll just assume not everybody does know how Java agents work. So Java agents are basically, you know, public static void main, but there's also public static void pre-main. And pre-main is a main method that's run before the actual main method. That's why it's called pre-main, right? But the great thing about Java agents is not only that it's run before the actual program, which would allow you to do some basic configuration, I don't know, set some system parameters programmatically. It also gives you an instance of the so-called Instrumentation API. And the Instrumentation API is like a low-level-ish hook into your Java virtual machine. It allows you to, for example, know when a class is loaded for the first time. And it also allows you to change the code of this class before it is set into production. It also allows you to redefine existing classes. There's actually quite a lot of things that are very useful to do. So what we do basically, we add a so-called class file transformer, which is then notified if a class is loaded, and a spoiler, for example, a servlet. And then we have a chance to add code to the servlet, and you can guess already how this works now, right? So for every class that gets loaded, we check, should this class be traced? And if it should be traced, then we should manipulate the code to add these sort of Sipcan calls to the implementation, right? So my job right now is to basically fix these two to-dos. Once I'm done with that, I can move on, right? So, and as I said, I wrote this library. It's called ByteBuddy, and it's an open source Apache 2.0 license. It's a quite mature library for exactly doing that. Bytecode manipulation isn't difficult, I would say. Bytecode is pretty straightforward. It's not like actual assembly. It's the Java virtual machine. I mean, if you guys, I was told everybody here is super hardcore and shouldn't even talk about bytecode. It would be an insult to expect that somebody doesn't know it. Just to be safe, it's basically, if you compile your Java program, it ends up being so-called Java bytecode. And Java bytecode is basically very similar to your original program, but it's a bit more machine typical. It's not machine specific, it's still cross-platform, but it's a more standardized expression of your Java program. And it's a bit similar like assembly language. It works with go-to statements, for example, but it's not really that difficult. You still have method calls, virtual method calls, and all these things. So yeah, it's basically an expression of that. So and with ByteBuddy, the advantage is you can manipulate bytecode without thinking about bytecode. You should ideally still understand what bytecode is, but in your daily work, you don't have to think of it. It's in a way, with Java, it's the same, right? You should still understand how a computer works, but you don't have to think about address spaces and all these things while you write a program. So you can focus on your actual task. That's what I would say is the main selling point. And this is how it works. Let's say you have this coworker that you really don't like, so you want to make this program work here. So you have a class foo with the method bar that just returns a string bar, but if you call bar, it returns hello world. And let's just write a Java agent for doing that. And with ByteBuddy, the agent looks like that, and please take me by my word, copy paste this code and it will run. So we create this pre-main method, which is put into a jar file, which you then on startup you write Java minus jar, and then you have your jar file, and then minus Java agent, and then you have the jar file that has this pre-main method in it. So it's two different artifacts. So and ByteBuddy has this API where you say, okay, we want to take every type that's named foo. So we have a matcher API there. So every type named foo, like the one above. Then we want to take every method that is named bar and intercept it to return the fixed value hello world. Then you install it on this instrumentation interface, which basically triggers the installation of a class file transformer. So this agent gets notified if this above foo class is loaded, then ByteBuddy looks for any method that is named bar and replaces its return value with hello world. So now your coworker will run this program, will set a breakpoint in the bar method, and there will be bar, but it will still trigger the assertion to work out. It's hilarious to put something like that on someone's Java ops while they're in the bathroom and see how they debug for a day or two. No, I'm just kidding, of course. But you see how you can also do useful things with agents, obviously, and distributed tracing is one of them. So I thought I'd just show you a bit how basically the instrumentations that we write look like. So for distributed tracing, I created a new component which is called advice. And advice allows you to add code before and after a method. So and it works with annotations. People don't always like annotations, but they are very, very handy for some use cases, and instrumentation is one of them. So we have this code here, which is just a standard method, and you annotate it with onMethodEnter, right? It's like aspect J almost, right? And you just add a single argument, which is the HTTP servlet request. And this will be the HTTP servlet request that is given to our servlet. So, and you also annotate this parameter, because you will actually never call this method, but it will be used basically as a template for ByteBuddy to add to your code. So, we get this zero argument, zero-based index, which is the request, and now we check for the trace ID. So we want to see, for example, X trace ID. So we now can check if a request is coming from another machine in our network, if we are continuing an existing trace. We also want to note down the method of the request, if it's a get or a post, or a delete or whatever, and we want to record the URI. And then if the trace ID is null, so there isn't any trace running right now, we just create a first one. Then we know, okay, we're serving an outside request, and we want to basically record how long it takes to answer this outside request and how many jumps we make in our internal network. And if it's already existent, this trace ID, then we continue our existing trace. Additionally to that, we have an onMethodExit method, and you can guess what that is. You get a response object. This is the second argument of the servlet API. And there we just say, okay, we want to now complete our request, and we want to record the status code that we have sent out. And this is then basically an annotation. So this code can now be added to every servlet in your application using a Java agent. So you have like a production team that just writes servlets, as they know, and then you have an operations team that has this agent developed, which once you add it to the app, will rewrite the code at runtime to add all this tracing logic that you otherwise with Sipcan would have to add manually. And the great thing is you can change any servlet. It doesn't even have to be your code. If you use a library, a third-party library that uses servlets under the hood, then this same code change would apply for that. You can even change Java virtual machine types. You can, if you want to redefine string, you can do that. It's not a good idea most of the time, but people do a lot of weird things. I would know because I'm contracting with Java agents a lot, and sometimes people ask you to do things you actually don't want to, but I guess that's consulting. Right. So how would you employ this agent? I already showed you how ByteBuddy works. So you would now just say, okay, we have every type that is a subtype of servlet. We want to transform, and there's this advice component I mentioned. We have this builder, and now we don't say we want to replace a method's return type with something, we just say advice goes to this servlet advice, and this is really this class, right? ByteBuddy then takes the servlet's advice and inlines it into every method that is called service. You probably want to be more specific about it, but it's good enough for demo. So now ByteBuddy would check every subtype of servlet, find every method called service, and just copy-paste the code, more or less, that you have in these advice methods in the top and in the end of the method. Right? And then you have what you wanted. This is what you otherwise would need to do manually. And the beauty of this is it's pretty safe. It's compiled code. ByteBuddy just takes the bytecode and basically translates the bytecode to match the actual method that you're instrumenting. So the parameters that you annotate, they don't even exist. They just map to the parameters of the original method that you're working with. Right? So this is how it works, right? Actually, there's more we can do. I mentioned already, you cannot only instrument types, but you can also redefine existing types. So if you have a type that's already loaded, then you can also change this code. And I already told you about pre-main. There's a third entry point to a Java program, which is called agent main. And agent main methods can be called while a Java process is already running. So you can come from a second process, you can find a Java process and go into this Java process and change its code and basically add this tracing stuff to an application that's already running. Other than pre-main, it's the same principle. Something we have to add two switches with ByteBuddy, which is the disable class format changes. The JVM doesn't allow you any retransformations, or at least hotspot doesn't allow it you. There's one VM out there that even allows you to change code altogether. But for our purposes, just adding code at the end and the beginning of a method, hotspot allows that. And the feature is called hotswap. You might notice from debugging. And we also want to tell ByteBuddy that it should retransform classes that are already loaded. So you have some production server, let's say, and it runs a bit weirdly, and you want to find out what basically is causing the issue, then you can add runtime without restarting the program, because then the problem might actually won't go away, but you want to find out the cause. So you can add runtime, throw in the agent, change the code to extract the information that you want, and then hopefully observe what's happening. And this is how we built our product, or this is how I built the agent that I was supposed to build. And here, basically, just what we do. Let's say you have this server, right? The server architecture, you have a PHP app, a Java app, and a JavaScript or Node app, and you run the system. So the agent that we wrote is that you have a backend, which is our trace collector. This is where all the information about spans is sent to. And then you install a small program on every machine. And I'm the contractor for the Java part. So I then discover all Java processes running on the machine. I discover all Docker containers that exist, and then I find all processes running in these Docker containers, and so forth. And then I basically go into these Java processes. I find everything I can, I go in there, and I change the code, instrument all known frameworks, and basically add this extraction mechanism for these traces that I need to. And then I can measure how long it takes to serve requests, how requests go through the network, and I can send this to the server. I put it on a Kafka queue, and the server reads it out. And the beauty here is also that I can then process the health of the system in a way. I know how healthy my system is. I know if you take 10 seconds to serve a single servlet request on one server, and there's 100 servlet requests coming in a minute, then I know you have a problem, right? And the problem with tracing is that it causes overhead. There's no such thing as a free lunch, right? So if you add this information, you have the I/O overhead because we have to send stuff out. We might, in worst case, even change the performance of the system because we add bytecode. By adding bytecode, we give the machine more to chew on. By making the machine do more work, it runs slower altogether, right? So that's the problem. But we can provide at least some feedback and say, okay, you know what? Right now it looks like this machine is on fire. We should probably do less work so we can retreat ourselves in the worst case, right? If I can tell you, you know what, your system is fucked, then I don't need to basically show you in detail. It's broken in all these places, I can just say like, okay, start here. I don't even measure that other stuff anymore, because then your system will fall over altogether. And by doing all this, basically you just can install a program. This is the only 2 product slides I'll have. I'll promise you, I'll just want to show you what you can get. You can get these distributed call graphs over different machines. You can say, okay, we have a HTTP request coming in, which yields another HTTP request, which then goes to Elasticsearch, and you can eventually see even, okay, this Elasticsearch call goes to these 5 clusters, and maybe you didn't write a good query, so you involve your entire network of clusters in just answering this one call, because you want some sort of confidence. Especially with Cassandra, this often happens. And you can also build these nice maps, which is, again, this is what WebSphere gave you already. Finally, we can give you back what WebSphere already had. You can see how your system interacts. You might even see the problems that you have in these interactions. And this is the idea. So, great. And this is how distributed tracing works. Right, so the rest of this talk, I'll try to explain to you some advanced topics. I'll try to explain to you what impact activating distributed tracing can have on your systems and what you might want to watch out for. And as I said before, I was told in JavaConf, everybody is a compiler engineer. So, and I'll try to find a middle ground, but yeah, this is basically, when you work with distributed tracing, this is what you will struggle with in your first weeks. So one problem is adaptive sampling. Adaptive is something that we do, at least. Adaptive sampling is that for every request that is made, we basically throw a dice. We don't want to trace all requests. Twitter does the same thing, for example. I think Twitter traces 1 out of 7 million tweets only, because otherwise the added overhead is so huge that they basically grind their own system. So we always throw a dice, and we either basically we say, okay, we don't need this, or we trace that, and we basically select those things randomly. We try to not spend too much time on finding out what traces we want to trace, but we try to still have some representational view of it. Once we trace things, we generate events, but we send these events to a queue. If the queue overflows, we don't want to create a leak or block the app, but then again, we might trash stuff. And this is the idea of distributed tracing. You only extract events if you really need to. If a system is serving 1 million requests a minute, then maybe it's enough to sample 1,000 requests. And maybe those are hopefully representative, right? But if you have a system that just serves 1 request an hour, then you really want to serve every single request, because otherwise you don't have a chance to see what's going on. So the trick is to find out what you actually want to see, without spending too much time on finding out what information you need. And to be honest, this is my biggest critique to existing APM tools. You know, we all love these dashboards, right? Where we see everything, every request, every header, maybe even the payload. But it takes time and energy and resources and processing power to generate these dashboards. And I mean, let's be honest. I click through these dashboards, it's like thousands of numbers, no human can process them. If you go into Logstash, it's like bam. And the trick is, if you can reduce this information, you make your machines do less. It's so easy. So I think, or this is what I think my personal mission is, that I try to see, okay, what information is actually useful, and the rest I'll just leave there, because then the machine can actually do what it's supposed to be doing. And it's not only about processing power. This stuff all needs to be sent on a network. And this, in the worst case, just costs you money. In the worst case. In the best case, just costs you money. In the worst case, this actually slows down your app. So we have this adaptive trace, and it's pretty steep. If you just have enough traffic already, it often is already sufficient to just sample a few events every now and then, and just to get a good representative view of what's happening, right? I mean, if you have like a questionnaire, then you don't ask everybody in the world to know what's going on. It's often enough to ask 1% of the population to get a representative view of the opinion of these people. It's just how it's happening already in the real world. I think this also applies for tracing. Also, people often ask, like, you have this tracing agent or this APM agent, and you ask, like, how much overhead does this add? I'm asked this question all the time because we have salespeople who get asked that by customers. And the honest question is, I don't know. I really don't. Because if you look at these two programs here, the right program on the right side, this will not have any overview, and 0%. If an app only handles web requests, then we will have much more overhead, because that's what we sample, right? So this is something to consider. There's no, and you will read this. I mean, I challenge you, try to go through marketing material. Everybody promises you maximum 3% overhead with APM tool vendor A. And that's just, if you just think about this for a second, this is just nonsense. Yes. And also, I mean, let's say you run it on your machine or you run it on a cloud infrastructure. If you have too much overhead, your machine will just burn, right? You will just crack your system. In the cloud, it might just run with 0% overhead, but with 3 times the cost, because Amazon spins up more nodes for you, right? So, one other thing, which is really difficult to get right, is so-called Chit-friendly tracing. The Java virtual machine optimizes your code based on the code it finds, right? And we are adding code to this machine. So, let's say you have a web request, then this comes from some native layer. And the native layer isn't optimized by the Chit compiler. The Chit compiler optimizes bytecode. But the actual handling with the network adapters is done by the VM in the C layer. So one good way is basically if a request comes in through the native layer, then goes through some Java code, then is answered again in the native layer here, then let's say this part is heavily Chit optimized. A good rule of thumb is to write good agents in general is to place yourselves on the outsides. Don't find a hot loop and paste in a bunch of code. You might drastically reduce the performance of your program. And this is not only because you change the semantics of the program, it's simply because you copy-paste bytecode in there. So if you do a lot of things, you will have to paste a lot of bytecode into the application. And the JIT works with heuristics, right? So big methods aren't optimized equally easily as small methods. And by copy-pasting code, you turn often small methods into big methods. So if you just go over some threshold somewhere, you might turn a really performant app into a really poorly performing app, and you might not even understand why. And it's simply because you're beating these heuristics. Nobody would write the code that you have created in the way that it is generated by ByteBuddy if you use it in the wrong way. So you have to be very careful. The more on the outsides you are, the less chances you have to basically disturb the optimization that is otherwise applied in the program. Also, if you add a lot of call frames, so you basically add indirections, the maximum inline level by default of hotspot is 9. If you add additional frames, you might just cut off some layer, right? So, ideally you don't break monomorphism. This is something that many people unfortunately do when they add new types also with instrumentation. How the JVM works is that if you have so-called monomorphic call sites, which are basically method calls that are done on instances of only a single type. So you have a list, and this list is always array list, right? If that's the truth, then Hotspot basically adds a direct link. It basically removes the virtual method call and inlines the code ideally. And about 90% of all method calls you do in a Java program, on average, are so-called monomorphic call sites. And they are very efficient. Then you have bimorphic call sites, which are basically 2 types. You have array list and linked list, where there's still a lot of optimization applied, where there's still inlining can happen. And then you sometimes read blogs where people claim there's more forms of polymorphism, but everything beneath in reality on Hotspot is megamorphism, which then yields always virtual method calls, which are much more slow than inline code. Not only because it's a virtual method call, but also because you might break more optimizations down the road. And your Java virtual machine is basically, it's constantly in movement. If your JIT finds that something can be made better after a bunch of runtime, it might do this. It might turn a megamorphic call to a direct link after it profiled this call site for long enough time. If you then come in later with the Java agent and you change the program in a way that this is not longer true, then at runtime, so we come in, instrument something, the JVM will de-optimize again, and even though you didn't change something, you might trigger down the road some optimization to no longer be applied. So you have to be very, very careful if you are, especially if you're a performance tool, because it's not a great tool to sell if you say like, you know what, your app's slow and it's because of us, then you probably will not sell much, right? Right. So how does ByteBuddy actually help monomorphism? These advice methods, as I said before, they copy-paste it. And copy-pasting doesn't help with method size, but it helps with monomorphism. Because if you copy-paste something, then you have the code at different places, and every code segment will be optimized in the way it is used exactly, right? So if you have the servlet advice, right, this parameter variable doesn't exist in reality, but all the code is then possibly specified for the actual instances of servlet requests, and this one as well. So this code will exist at multiple places in your app in the end. If you have written it manually, you would try to write nice code, right? You would try to abstract it away, and you would have some generic dispatcher somewhere, because you don't want to repeat yourself. With ByteBuddy, mostly accidentally, you can do both. One other very important thing, and this is really something I don't understand, because I think Twitter is a big company with a lot of competent engineers, and I don't understand why they get it wrong. Twitter uses a lot of Scala. And Scala is, nothing against Scala, but Scala doesn't know primitive types. And they sell that as an advantage. But the problem with Scala is that it's still run on the JVM, which is pretty much aware of primitive types. It's a different type. Simple as that. So Scala, in a way, has to box everything, which it cannot prove at compile time to be non-nullable, right? Nullable. So if something's nullable, you have to add a wrapper. And in Java, the spans that Sipcan generates, because it's a Sipcan-based library, a Scala-based library, and there's a lot of stuff that's boxed. So we know that we have a trace ID, but we, for example, don't know if we have recorded timestamps. So timestamps, due to the Scala compilation, are nullable and don't have like just a zero value, a natural zero value. Like a timestamp of 0 is non-meaningful, or of -1, right? So you can use that as a null alternative. And this generates, unfortunately, a lot of garbage. And that's why Zipkin is actually adding quite a lot of GC time if you use it. Because if you always assign these boxed values, a lot of objects will be allocated, very short-lived objects, but they will still be allocated. They will trigger young GC. And I had a tweet recently where I ran into a problem. I'm not yet there that I'm confident to say that I really know the answer. But if you have a program that generates a lot of short-lived objects, then these objects will not generate too much GC because they die quickly in the young collection. If you add an embedded program into the same VM process that burns object at an even higher rate, then you have very, very short-lived objects, which then changes the semantics of the normally short-lived objects to be much longer-lived than the new shortest-lived objects, to become long-lived objects as a consequence, right? So you, again, can, by little changes, change your GC rate drastically. And a very, very simple optimization we did in our tracer was to not allocate objects. I mean, it's a simple recipe, and it's so easy because, as I said, a timestamp, if the value is 0, that can be just the same as saying it's null, but you save yourself from it. And that's why I never understood why Scala is used in these high-performance systems. It's, in my opinion, just this primitive type thing doesn't work out often. So, yep. The same goes for lists. Linked lists, as in many like immutable languages is, and that's the other thing. Immutability is terrible for performance because you have many, many short-lived objects again, first of all, and then like linked lists, they distribute over your heap at different locations. You just ruin your caches, your processor caches, because you don't have arrays. Arrays are nice. Arrays are efficient. All these immutable lists, they have to build upon the previous lists, and then they end up at different places. That's unfortunate, but it's simply as that. So in our tracer, everything's mutable, everything's primitive. We use object pools to avoid GC. It's a very old-fashioned programming approach, but it works pretty well. And this is so-called memory-friendly tracing. So yeah, I think I'll jump over this slide. It's just a comparison that's not so important. So yeah. Also, I mean, in the end, we have to write plugins for all frameworks, right? So we have support for servlets, I mentioned that, and we have support for all the fancy stuff, Elasticsearch, Cassandra, everything that's the hype. EJBs, I wrote Corba instrumentations, which almost made me quit because that was a piece of work. But we can't cover everything, right? So another nice thing with these distributed traces, this instrumentation traces is that, again, we can use annotations. We can, for example, discover SDK annotations. If you just annotate a method, then we can know, okay, we need to instrument this method too. And then we know, okay, you have this foo method here, and we just add code in the beginning and the end. So you can also extend it by that, and the nice thing is that you as a developer, you only need to know that there's an annotation. You don't need to know how tracing works altogether. I just say, okay, this is an interesting method, so I want to record once we trigger a batch. One very difficult job, and another reason why I think that the Sipcan approach doesn't really play out on the long run, is that Java is a concurrent platform. Let's say you have a reactive framework, and you are receiving a request from one thread, but you're serving it on another thread. And then while you haven't served it, this one thread is already used for something else. And think of Akka. In Akka, you cannot really say, I enter here and I exit there, because it just pings through all of your systems. So whenever you have a context switch in your application, you have to basically notice that there's a context switch and basically translate this current span to this other thread. So if you have like a thread pool, whenever there's an execution, you basically have to inherit the current span that you're doing. And OpenTracing has APIs for that. So OpenTracing doesn't only require that every basically database tool, every HTTP tool, everybody who's doing entering and exiting of a VM implements the API. They also require that every single concurrency framework in the world adds hooks into OpenTracing. And I just don't see that happening. That's why I'm so for the instrumentation approach here. Some other things you will have to deal with are security managers. And Elasticsearch is a good example, which, if you run a server, uses a lot of security managers. Actually, they implement their own security manager that doesn't even respect all policies you set, because they think you can crack it. The good news is, with instrumentation, you can just instrument the security manager. So we have something like this. So we sandbox the security manager to basically allow our own calls to go through. So these access exceptions aren't thrown anymore, so then we can happily go into a Elasticsearch box and do whatever we want, and you cannot forbid these things. Instrumentation allows you to break through everything. That's what makes it very powerful, but makes it also very dangerous. So this sandbox thing also took us a while to get right, but now it works really neatly. Yes. So, final slide already. So how do you test these things? This is maybe the hardest part about it. But thanks to modern container technology, this is actually also quite straightforward. So let's say you have an app that communicates with Elasticsearch, and you want to measure that our instrumentation works with different versions of Elasticsearch and different driver versions of Elasticsearch. So then we just start a Docker container. Within this Docker container, we just drop in our agent. Then we just have a JUnit test. From JUnit, there's a great framework. It's called testcontainers.org. Allows you to spin up Docker containers or images from a unit test. And then the jar has just a main method. We just execute this main method in a Docker container. We have a hook for that. And then our agent is in a way stopped to send events back. Right? And we just validate that all the events that we expect are actually occurring within this containerized environment, because this is super predictable. We know the data that's in there. We know the exact environment. And we can actually just change a few numbers, and then we can just run a matrix of all versions that we care about and validate that it always works. And this is how you generally can test agents very nicely. Just spin up a container with a Java app, instrument this containerized environment of which you know that it will be the same environment everywhere, and validate some outcome or some exiting state within this container. And as I said, testcontainers.org, open source project, works really nicely. All right, and that's all from me here. So if you're interested in this sort of stuff, you can find me on Twitter, where I sometimes tweet incomplete thoughts and sometimes links to stuff I do and work with. Please check out ByteBuddy, Apache 2.0 licensed project, bytebuddy.net or on GitHub. Also I have another open source project called Documents for J, which are basically Java adapters for .NET to trigger the Microsoft Office APIs. So it allows you to interact with Office, like mostly for conversion purposes from a Java process. Right, thank you so much. Thanks for coming.
Thanks, Rafael.
Are there any questions? I have 4 minutes left. Other than that, I think there's
sure.
like a question.
We have time for a few questions, and after that, you will be able to find Rafael in the discussion zone and talk with him more.
Thank you for the talk. And the question is, well, when you prepare ready for Go agents that are good for one version of the application, how would you ensure it won't break in further versions? Or how would you approach the thing when you deploy your application, it works fine with Spring 3.0, and when you upgrade to Spring 4, you need to, I don't know, have two agents. How do you deal with that?
Yeah, good question. Actually, this is tough. We code very defensively. So first of all, we validate the type hierarchy. So we check if the methods that we require actually do exist before we instrument, and if we don't find methods, like for example, the old servlet API didn't have a get status code method. If we find out that this method doesn't exist, we just have another advice class that is compiled against an old version, and then we inline that other version instead. So we might offer lesser insight, but we won't break anything. Yes?
Yeah, if nobody minds, I would ask another question. Well, you mentioned that the tough part is making the results good. So can you please name like the best feature you have? So what is the main point APM should show? What is the, say, the rule, the silver bullet of APM dashboard?
I mean, there's no silver bullet. Obviously, it's opinionated, right? So I think the most important part is already just to show how the network of services, how that looks like, right? But generally, it's like we have customers, right? So they say, we would like to see this sort of information. And then I say, yeah, sure. That's pretty much how the development process is. So, I mean, it's user stories, but yeah, there's no silver bullet. It's always a trade-off, and I'm not always happy with what people like to see. I say, like, how is this information useful to you? I don't see that, and this will actually burn cycles. So, are you sure you want that? And it's like, yeah, we want that, and then sure. But it's also like you could make these things customizable, but then it's again a trade-off between how complex the product will be and how easy the instrumentation works. But now that there are no silver bullets. I mean, the slide ahead said there are no silver bullets. And it's basically, it's also water on the hot stone a bit. Microservice networks are complex to maintain. They're complex to operate. Sometimes traces aren't correct in any tool because we forget some mechanism. We have overlooked something that interacts with each other, or we correlate two interactions that aren't actually bound to be together, but we misunderstood something. So there's no guarantees, but never in software. I mean, there's always bugs. I'm sorry, is that an answer to your question? It's difficult, right? Can't say anything against that. Yes?
Now a question? Yeah.
I'm not quite sure. You described how often do you store the data, the tracing data to, in your case, Kafka, right?
Yeah.
are there any different strategies, modes to store per single request, or just for one request and pass all the required information from request to request?
I mean, we batch them, obviously, but there's also, again, you have a trade-off. You want to send it not too late, because people look at dashboards and they want to see live data, right? So they want to look at it, they click a button and they want to have it appear. If you wait too long with the batching, that will take some time. So we have like bursts, we collect data. If we see there's a lot coming, then we just concatenate. And then maybe then it suddenly pays off to zip the information before you send it, and then there's less data. If there's only little data, the zipping doesn't pay off because it's more processing power you need, and the savings aren't so big. So it's, I would say, a reasonable mechanism, but in the end it's not that complex. We just batch it, and then every 1 or 2 seconds we send, or we append to the Kafka queue. But we do it asynchronously, so we don't do any work from user threads, and we also down prioritize. And that's what I meant with this adaptive sampling. If we feel like the system is already on fire, then we retreat a bit. Then we say, okay, you know what, right now is a potential fallover point. We don't want to get involved too much right now, because then we actually, our monitoring work might make the system fall over. So like this is, we have these queues, and we use JC tools, if you know that one, which allows you very neatly to avoid overhead when you communicate data outside without having to check if there's suddenly too much work from all threads. So that's what we do.
Okay, so am I getting you right? If I have a very, very long chain between my services, I mean a lot of requests choreographed between different microservices, then it comes to very, very big payload because of tracing information.
I mean, in generally that's true. The more you trace, the more payload you add to your application. So what we do is basically we limit the maximum payload we add by stopping to trace additional requests. Like if you're serving 1 million requests a minute, then we might trace 10,000 requests. If you have 10,000 requests a minute, then we might sample 6,000 of these requests. And you have like an effective sampling rate of 60% in the low load case, and you can still see, like, let's say you have a tool that only has 1 request a minute, then you will probably see every request. What we make sure is that every trace is complete. So we don't like say, okay, this call is causing a JDBC call and an Elasticsearch call, and we just drop the Elasticsearch call, you will only see the JDBC call. That doesn't happen. You will always see complete traces, but you will not see, if you have 1 million requests a minute, you won't see 1 million requests in your API, your GUI, right? So then you will only see those that we sampled, and I would say that's reasonable because nobody goes through every request if there's 1 million a minute. So that's the idea. But different vendors have different strategies. We try to not overflow too much, and so both limiting memory usage, because if you keep them in memory, you use heap, right? So we have thread local buffers first. Everything goes to thread local buffers. Those are then flushed to a application global buffer, and then they flush to the backend. That's more or less the queue. And if at any point we notice, okay, now there's just too much data collected, then we scale down or throw away events already.